Okay, welcome to class meeting 3 or Introduction to Optimization Theory. We have homework now assigned, probably. Someone already uploaded or you are going to? Yeah. So the homework 1 is assigned, uploaded on the course webpage. It's due in 2 weeks. Okay. So sometimes the homeworks will be assigned in every 2 weeks, or sometimes the due will be 2 weeks. But sometimes they are not, okay? So you may have one more homework next week. By the way, these are all based on the 3rd edition. And the TA will also mark the corresponding problems in the 4th edition. So you may have 4th edition of the textbook or the 3rd edition. Okay? What we are going to today is to very, very quickly cover chapters from actually 1 through 5. Okay? Very fast. So actually, these are the keywords you need to know in the chapter 1. The chapter 1 has the title, Methods of Proof and Some Notations. Some notations, I should. Yeah, anyway, some notation. First, you have to distinguish the 2 English words, denote and notation. Actually, they are closely related, like this. For example, A superscript capital T, but actually this is not a superscript. It's kind of, sometimes you use alphabet T, but in this textbook, it used just a figure, like looks like T. Okay, so it depends on your choice. But anyway, so we may say that A sub T denotes the transposition of A, and the notation for a transposition or transposition of A is this one. Okay. So you see the verb denote and the noun notation here. Okay, be careful. Sometimes definition looks like notation, but precisely speaking, they are different. Okay. For example, in many cases, especially in this lecture, I will use this notation to denote a column vector. Got it? But column vector is, by definition, is a collection of finite numbers, finite number of, in this case, real numbers, which have orders. Okay? So in that sense, we cannot easily distinguish a column vector from a row vector. We need more quantifier to define a column vector. But what I want to say here is that this is not a definition of a column vector. This is a notation of a column vector. And if you really want, for example, if we write it this way, then you may say that this is the definition of a column vector, and this is the notation for the column vector used throughout this course. Got it? By the way, in our textbook, to denote a column vector, the author uses boldface alphabet, lowercase. But it's not easy to handwrite that, so I will adopt this notation. Lowercase alphabet with underline. Okay. By the way, we Koreans say underline, but actually this is kind of underscore or something. But anyway, it doesn't matter. Got it? So this is the notation, and this is the definition for column vector. Got it? Okay. And the rest of the textbook talks about the statement And in Korean, it's translated to 명제. Okay, I do not remember the Chinese characters. But anyway, the statement is what? Statement has a property. Okay, statement must have a property that we must be able to say whether it's true or false without any doubt. Got it? So, statement is either true or false. It cannot be both. Okay. So, sometimes we have a truth. Sometimes, by the way, we combine more than one statement to have a new statement. When we connect them, we use and, or, not, and others. Okay? Usually, and or not is enough to have every possible logical combinations of statements. So, such a combination, which is a new statement, is called a combined statement. Sometimes it's not easy to directly see whether this new combined statement is true or false. That's why in our high school we introduced the truth table. Okay? For example, suppose we have two statements P and Q, and new combined statement P and Q. Okay? Then the statement P may be true, okay, depending on, this could be arbitrary statements, okay, may be true or false. Unlike what we did in our high school math, this textbook starts from false, false, I don't know why, then false, true, true, false, and true, true. In that case, our intuition says that if both of the statements of these combined statements are true, then this is true. Okay. If at least one of the statement is false, then they are false. Okay. So this is the truth table for the combined statement P and Q. Okay, and whether a statement in this form is true or false depending on this component statement's truth or falseness. Okay, like this. Got it? Now, let me talk about conditional statement. What is a conditional statement? Conditional statement is in the form like this, as you've seen in your high school math. Okay, it's a kind of combined statement, but to combine these two, we do not use and or not. Okay, this is called implies, or this is and sorry. Not this one. The other one is called implied by. Okay? Or sometimes this means if P, then Q. Okay? And this is P only if Q. Okay? So this is a new statement, and also this new statement is quite intuitive, has a very quite intuitive truth table, except some lines. But if, as you've seen in high school math, if you draw a truth table, then you have this. So what is unintuitive? If A is false, then this conditional statement is always true, and if both are true, then it's true, and only this one has false. Okay. Now, one interesting thing is that this conditional statement has the same truth table as what? As you've seen. Not P or Q. Not P or Q. Okay. By the way, this one usually 수학의 정석 adopts means and this means or, and this means not. Okay. And if you plug in this false and true, you will see that you have the same thing. Okay. So these two truth tables link a combined statement and a conditional statement. Okay. So in that sense, these two statements are equivalent. Okay, got it? And by using these two and combine these two statements, see that this is a conditional or a conditional statement. This is another conditional or another conditional statement. Now let's combine these two statements using and. Then what will happen? We have a new combined statement, and the notation we adopt is this one. Got it? So this is a new notation. Okay. Got it? Now what is the definition? This and this. Got it? So I'll just briefly talk about the terms, the verb denote and the noun notation, and have given you some kind of English translation of what you learned in the set theory of the high school math. Actually, this comes first, and then probably the scholars, Japanese scholars in Meiji era translated these English or sometimes German or French mathematical terminologies into Chinese characters, and many of them we still use. Got it? Okay. Now, in the last part of the section 1.1, the authors talk about proof of methods, okay, proof methods, and of course there are many different proof methods, but the most famous ones are these direct proof. Okay. So direct proof, so proof methods to prove such a conditional statement. Okay, suppose you want to prove some conditional statement. P implies Q. You want to show that, for example, this statement is true. Okay, what do you do? So in the direct proof method, you start from the truthness of P. And what you do is that this truthness implies truthness of another statement, another one. So implies, and eventually it implies Q. Then we have proved this conditional statement using the direct proof method. Okay? Got it? Okay. The second one is proof by contraposition, and it's very confusing because they look very similar up to this, right? Contra. Okay. The third one has name proof by contradiction. Okay. They are looks almost the same, but they are different. Okay. You must be careful. In order to know what is a proof by contraposition, we have to define the contraposition of a conditional statement, okay, or contrapositive of a statement. So suppose that you have a conditional statement P implies Q. The contrapositive or contraposition of this statement is what? You change the order and you put this not sign. So you negate the truth or falseness of two statements. Okay. So this statement, not Q implies not P, is called the contrapositive of this conditional statement. Okay. What is the interesting thing? As you learned, by the way, in Korean, old 수학의 정석 says that if this is a statement, this is 대우. Okay, probably this is also a translation by Meiji scholars. Okay. Anyway, the interesting thing is this: suppose you use Korean Wikipedia, and you find you search for example, 대우 here. Okay, and you see the Chinese character, and you have a lot of alternatives in different language. You click Japanese. If you find they use the same Chinese character, then it's highly likely that that translation is from the Meiji era. Okay, and more interesting is that if you click Chinese, and if they use that, okay, Chinese also adopted the Japanese scholars translation. But what I have found so far is that those Chinese guys really hated Japanese translations, so it seems they changed it a lot. Okay. For example, the recurrence, JV, okay? If you find, or for example, difference equation, okay? As you learned in signal-gen systems, linear difference equation. In Korean, we call 차분 방정식. And probably Japanese pronunciation is almost the same. They use the same Chinese characters. But if you click the Chinese, then you will see totally different Chinese character. Okay. Anyway, so here, what I just want to say is that that even you do not know what kind of Chinese character is used. Okay. Actually, is the translation of the contrapositive. Okay. Contrapositive. Okay. And they have the same truth table. Very interesting. Okay. So what is then proved by contraposition? For example, suppose you want to prove that this conditional statement is true. What does that mean? If P is true, then Q must be true. Suppose direct proof seems difficult. You start from P and implies P1 implies P2, and eventually you want to imply Q is true. But sometimes it is easy to use, for example, direct proof method starting from not Q. What does that mean? Not Q is true, which means that if Q is false, then implies P is false. Okay? If you can prove that, since they have the same truth table, actually you prove the original conditional statement. Got it? That is the proof method by contraposition. You use contrapositive instead of the original conditional to directly prove it. Okay? Got it? Now then, what is the proof method by contradiction? What is contradiction? Sometimes they look almost the same actually, but it is not. Okay? Contradiction is this. You want to prove anyway P implies Q. But you know that, as I just told you, it's the same as not P or Q. So if you want to prove this conditional statement, it's equivalent to prove this statement is true. Okay? But that is not proof by contradiction. Proof by contradiction is to prove the negation of this one, not of this one, is false. Okay? Got it? So you want to prove this is true, which means that the negation of this one is false. That is proof by contradiction. So what you do is that you show P and not Q is false. Okay? This is proof by contradiction. So anyway, you start from the truthness of P, the first statement. The difference is that P combined with falseness of the statement Q must be false. Got it? Because it's kind of obvious. If P is true, Q must be true. So if you assume P is true and Q is not true, then it must be an absurd statement. Okay? So that is proved by contradiction. Okay? So today now you clarify the difference of these two. Okay. Anyway, another method, there are many other methods. Okay, there are many other methods, but one of the methods I didn't have written down here is the mathematical induction, as you learned in high school math. 수학적 귀납법, translated in Korean. Okay. By the way, there is another similar thing with mathematical induction. Mathematical induction usually starts from this. This statement is true for the first subparameter n equals 1, for example. And then, second, you prove that if the statement is true for some case, then it must be true that the k plus 1. But, so in that sense, it only holds for some, if after mapping some countable number of statements, right? The first statement, second statements. There is another one. Okay, I forgot the name. Okay, it was not mathematical. It trans some induction. Okay, I will find that. But anyway, there is a similar proof method to the ordinary mathematical induction, but that is for uncountable number of statements. Got it? Okay. Okay, so that's all for section 1.1, and section 1.2 is about the notations this textbook adopts. So you read it, okay? Anyway, you need to get acquainted with the notations used in the textbook to read this textbook, okay? Okay, I will not emphasize anything, you read it, okay? Okay, any question about this chapter 1? Okay, then let me move to chapter 2. From chapter 2 to actually up to chapter 5, I'm going to use our lecture note. Okay. So this is the lecture note for the mathematical review, and as you see, it starts from the review of section 2.1. Okay. That's why I have written down some important facts, definitions, and notations you need to remember on the board. Okay. When you read this lecture note, okay, this PDF, what I advise you to do first is that you draw straight lines, okay, to group them into each chapter. Okay, so here, if I were you, I will draw a line here and say chapter 2. Okay, because otherwise it's very hard to which chapter you need to look up. Okay, but anyway, as you see, very kindly the author, the Professor Chong, put the section mark. So up to here it covers chapter 2, and from here it covers chapter 3. Okay, what is the title of the chapter 2? Chapter 2 has the title Vector Spaces and Matrices. So it's about linear algebra. Actually, chapter 3 is also about linear algebra because it has the title the transformations, especially linear transformations. So the authors talk about eigenvalues and eigenvectors, and also they talk about quadratic transform called quadratic forms, and you already learned. So chapter 3 is all about linear transform and quadratic form. Of course, he also talks about matrix norms and vector norms, and they are also important, but he didn't include that matrix norm part here in the lecture note. And as you see that this is section 3.4 with quadratic functions, as I just told you. Okay. Suddenly it jumps to section 5.5. Okay. So here there is a huge gap. As I just told you, you need to review some definitions of vector norms and matrix norms, which are the topics of chapter 3. And here, the entire chapter 4 is missing. Okay? That does not mean chapter 4 is not important. Okay? Chapter 4 is also important, but what I have found, actually I read chapter 4 this morning, and chapter 4 is much easier. Okay? You can read yourself. Okay? Nothing difficult is there, but you have to read. Got it? Fortunately, this Wednesday is a national holiday, so we will have next class meeting in 1 week. So you have plenty of time actually. So you read those chapters and also do your homework so that you will be well prepared for the chapters from 6. Okay. Anyway, here, if I were you, I put chapter 5. And chapter 5, from chapter 5, actually chapter 5 is related to calculus, especially the multivariate calculus you learned in your undergraduate program. Okay. Especially the notions of continuity of a function, notions of the differentiation of a multivariable function is very important. Okay? So if you do not remember some of them, read it. Okay? Anyway, this is an overview, and let me start. I hope you have all printed out this lecture note. Okay. So the notations are exactly the same as what is used in the textbook. Okay. This R denotes, okay, as I just told you, this R denotes the set of all real numbers. Okay. R superscript n, I will say R to the n or Rn, denotes the n-dimensional Euclidean space with real entries. So if we view this as a set, it has elements or members. I prefer members, okay, because there is a set and there are many members. Elements means something like elements in chemistry, so I do not like, but somehow people just say a set has elements, okay. By the way, we denote the set of this R to the n set by this boldface lowercase alphabet. Okay, and this is especially a column vector with n components. Okay, so this is another confusing terminology which I really hate. But anyway, so chapter 2, you have to know that the difference between member and element or members. Okay, are they different? Actually, same. Okay, it's like X is a member of R to the n, or X is an element of R to the n. But so they are the same. But suppose you have a vector X, then you want to say that ith something. Okay, in that case they use a component. Okay, for example, if you have X looks like this 2 by 1, then X1 is the first component of X. Actually, I really hate this terminology. Okay, because there is another one which fits better. By the way, to denote matrix, the authors use uppercase boldface alphabet like A. The problem is that it's not easy to write boldface. Okay, so sometimes I will use like this, but it's confusing because this typeset is reserved to denote some set. Okay, so I will try my best to be consistent, but do not expect much. Okay, anyway, suppose you have a matrix A. Okay, so this is the notation to denote the matrix. And what are these? Usually in the mathematical books, they are not called components. Okay, they call them entries. Okay, so 2 is the 1/1 or 1/1 entry of the matrix A. Okay. And you all know that vector is a special form of a matrix. So myself prefers using entry. So I may say that, okay, first entry of vector x, this is the second entry of vector x. But you will see many professors and research papers and other books will say that this is the component. Okay, so what is this one? Given a vector x like this, what is this one? They say that this is a notation for a vector that has component-wise negation of the of the vector. Okay, but I will say that it's entry-wise multiplication with -1. Okay. Anyway, so this is a kind of the more conventional way. For vectors, these are components. For matrices, these are entries. Okay. Okay. What else? Let's move to the lecture note. So as you've seen, so let's extend this notation. Okay. Here we have superscript that has two numbers with this times sign or cross sign. We call it r to the m by n. Okay. You may say the n times n, but usually r to the m by n. And this is a set of all m by n real matrices or matrices with real valued entries. Okay. And here this m is called the number of number of rows. Okay. And this n is called number of columns. As you see, that this is the first row. This is the second row. So you see the entries in the first row has the first subscript all ones. Got it? So the first script is the index for the row. Second subscript is the index for the column. By the way, you want to clearly now know the difference between superscript and subscript. Superscript. So suppose you have some notation like this, or notation like this. When we use superscript, we usually use parentheses or round bracket because sometimes otherwise we cannot distinguish from the power from the index. Okay, so it's like, suppose I use superscript like this. Does it mean some second entry or component of a vector or x squared? Okay, so for the superscript, these are called superscripts. Okay, the small characters placed on the right or left upper part. Okay, so in order to differentiate, distinguish the power, from some indexing, we use usually the parentheses. But for the subscript, sub means low, right? Below. For the subscripts, we usually do not use parentheses if it is really necessary. Okay? Because anyway, the most important thing in the notation is simplicity. Okay? So as far as some notation does not inflict any confusion to us or to the readers of the textbook, then we just drop. Okay? So that's why here I just used numbers. Okay? But if I use the superscripts, probably I used parentheses. Got it? Anyway, for Korean students who raised in Korea, at least you need to clarify all these things in one of your courses. Okay? And probably today, I hope, becomes that course and that class meeting. Okay? By the way, this R to the N or Rn, okay, actually it's kind of power, or you just say that R sup N, because this is superscript, right? Okay. Anyway, this can be viewed as some kind of power, okay, if you want, or some superscript. So in many cases, people just say Rn, okay? It's not a power actually, but sometimes people say R to the N, okay, as I do in many cases. Or some people say R superscript N, but superscript is too long. Anyway, there are two types of scripts, super or sub. So in many cases, I would say R sup N, okay, superscript, and I just drop postscript and sup N. Okay. Anyway, R sup N by 1 is actually the same as R sup N. So in many cases, we just write this way without N by N. Got it? So they are the same set. And as I just told you, matrix transposition is very important. So we introduced this notation, but here in the lecture note, he used capital T. But if you look at the textbook, he do not use this alphabet T. He used some symbol, looks like T. Okay? Anyway, so a transposition, as you know, it's 전치행렬, right? Is it correct? Yeah. So you change the place of an LMth entry with ML's entry. Okay, so the transposition of 1, 2 is the row vector is a column vector. By the way, I want to emphasize this one. In MATLAB, okay, you should be careful in using transposition, ordinary transposition, and Hermitian transposition. I've seen too many mistakes from my former graduate students when they handle transposition and Hermitian transposition in MATLAB. Transposition is like this. Suppose you have something like this. Okay? What is the transposition? You just change the LMth with MNth, like this. What is the Hermitian transposition? You not only change the LMs with MNs, what you do is that, what? Yeah. You put the complex conjugate, okay? So except these diagonals, right? Am I right? Except the diagonals. Is it correct? Including the diagonals? Yeah, including, I guess. So in this case, they are real. Okay, then let me be careful like this. This would be better. Okay, so minus j. Okay, yeah, I believe I have to put conjugation anyway. So here we have j minus 2j, and here minus 5. Okay, So we put conjugation. Now, suppose this one is A in your MATLAB. Then, what is the transposition and what is the Hermitian transposition? In MATLAB, this is Hermitian transposition, and dot apostrophe is the transposition. Okay? So be careful. Okay? Sometimes you just want to change a row vector into a column vector. In that case, you have to use dot apostrophe. I had some experience like probably Taejun or Jung-hoon found that my already graduated students' MATLAB code has this mistake. And I wondered, hey, how did he graduate with this bug in the MATLAB? Anyway, I didn't retract his degree yet. Okay, so be careful. Never make this mistake. Okay? Very, very important. But to do your MATLAB homework, probably there will be not that many, but some. Okay, it's okay because all the problems in this textbook only involves the real valued vectors. Okay, so they are the same. But after this semester, probably you may just have a bad habit of just mixing these two. Never do that. Got it? Okay. Never blame me. That's why I'm emphasizing this. Okay. So we've done up to this one. Now functions. I still remember. I still remember when I became a middle school student. Okay. In the math class, my teacher was talking about a function. Okay. I really felt uncomfortable about this term 함수 function in Korean because he did not write down the Chinese character, and he said that actually this is a kind of adoption of pronunciation. Okay, so it's like that terminology 함수 was not a Japanese Meiji scholars translation. It was a translation of Chinese people, Chinese scholars. Okay, and they had no idea how to adopt. Actually, by the way, whenever you see some terminologies that just borrows the sounds, it's highly likely that it's by Chinese scholars. And if you see some terminologies that really tries to have the original meaning of the terminology, it's Meiji Japanese scholars. Okay. Sometimes you get amazed by those Meiji scholars, but they were not perfect. So they made many mistakes. For example, our terminology, 유리수, 무리수, that are translates from, those are translates from rational numbers and irrational numbers. So since those scholars didn't have enough knowledge, so actually rational number is not related to any reasoning or rational thing. It's kind of number that can be written in the form of a ratio of two integers. In that sense, it's rational. But when they translate, they've seen probably some other texts in, for example, philosophy or logic. And rational means what? 이성적인 in Korean. So they probably translate into 유리수. But actually, in Korean, that must be, or in even Japanese, that must be, I believe, translated in 유비수. Okay? Because it can be written in the ratio B of two numbers. So 유비수 and 무비수 may be better translations. But anyway, they made some mistakes. But in many cases, you get amazed. Okay? Very, very probably they spend their entire life for the translation. Okay? Anyway, so this function is written in this form, and some of you still, I hope not many, but are not familiar with this notation. What does this mean? You have a function named f. Okay, so this is the name of a function. Okay, and this colon separates name and the function's property. Okay? What is this property? Your function is defined in the domain X. Okay? And your function value is a member or an element of this range set Y. Okay? Got it? So let me repeat. This is called the domain of the function f. Okay? And this set is called the range of the set Y. Okay? Okay, by the way, you want to distinguish some other terminologies. Okay? So the function's name. You are talking about the function's name. This is domain of the function. This is the range of the function. In Korean, probably this is 정의역 translated as. This is 지역이었나요? 공변역이었나요? 예? 공역? 공역. When I was a student, it's 공변역. By the way, this is a new notation. See that? This is wrong actually, because f can have an argument that is a member of this set. Okay? So f cannot have this entire domain as its argument. But this is a new notation. Okay? This does not mean you evaluate f at every x or any x. It means that it's a collection of the set. So this notation means the set of all f of x such that, by the way, this reads such that x in the domain X. Okay? By the way, this is different from range. Okay? It's usually a subset. Okay? It may be proper subset of range. So this is called image. Okay? The image of F. Okay? Got it? So image of X. Okay, image of X via F. Okay, something like that. Okay, anyway, it seems I'm too slow. But this is important. Anyway, you have to do it at least once. Okay, or some of you who were taught math courses in English probably already know. But when I was a graduate student, okay, 20 years ago, I suffered a lot because at that time there was no undergraduate courses offered in Korea in English. So I had no idea what is the English terminology corresponding 정의역 or 공변역 or 공역. Okay, that's why I'm doing this. Is it helpful or you already all know and waste of time? It's okay? Okay. It's too slow right now. I have 8 pages to cover and still working on the first page. 큰일이죠. Okay. Now, so as I told you, f takes values in x. Exactly speaking, the argument of x. Okay. The argument of x takes values in x. Okay, actually, f, not f, but anyway, usually we just say for simplicity, we just say f takes value in x. And f of x is what? Has value in y. Okay? So what we call is that y is, f is y valued. For example, suppose y is the set R, the set of real numbers. Then f is called a real valued function. Okay? So write down here some example. Okay. For example, let's see this one. What is f? F is a real valued function. Got it? Okay. F is y valued function. F is real valued function. Okay. And now let's take a look at this function f. Okay. In mathematics, we only allow single character for the function's name, but in MATLAB, I really like MATLAB. They allow more than one character. Okay. So in writing MATLAB codes, you need to devise of course it also introduces some confusion. Okay. So you have to devise a way to distinguish a function's name from a constant's name. Okay. When you write the code, be careful. Sometimes people use capital letters, okay, for the constants. Anyway, section 2.1 talks about a linear independence of a set of vectors. Okay. And from here, I'm not going to talk everything. Okay. Otherwise, I cannot finish 8 pages today. I will just point out what are important. Okay. So whenever you see something like this, okay, see the left-hand side, product of a constant and vector. Sometimes this type of thing looks like product of constants and constants. But anyway, so what is important is that it's a summation of products. Okay? So from right now, whenever you see something in the form of summation of products, write it in the inner product form. Okay? So try to write this in an inner product form. What do you have? Do it right now. Do it right now. So as you see here, you can write it this way. This is a kind of inner product form, right? So you multiply A1 vector with alpha 1 constant, A2 vector alpha 2. Okay? So you can write it this way, or you can write it as a transposition of this one. Like what? Can you do that? It's not easy. Okay, probably this is the best way. So linear. What does the linear independence mean? So given a set of vectors, okay, if this equals 0, this equals 0, if and only if this vector is 0, then they are linearly independent. Okay, so since this is true, linear independence means that this alpha vector equals 0 vector. Okay. So the only vector alpha that can make this inner product equal 0 is the 0 vector. That is the linear independence. Okay. Anyway, you read it. The details. What I want to emphasize is that in this course or afterwards, in every signal processing and communications courses, you have to be able to write transform this way. Okay? Especially when you write the MATLAB code. Okay? Because suppose you write the MATLAB just translating this one. Probably you want to use a for loop. It's a very bad idea. Okay? MATLAB is not good to have nested for loops. Okay? It becomes very, very slow. Okay? So whenever you see something like this, define a new matrix A and new vector alpha and just do the matrix vector multiplication. Okay. Okay, next one. Rank over matrix. Okay. This is the definition from linear algebra. What is a rank? Okay. It's a property of a matrix. Okay. But remember this way. It's a property of the column vectors of the matrix. Okay. Originally. Okay. Because the definition of a rank is related to the linear combination of these columns. Okay. So as it says, the maximum number, or maximum number if you want, of linearly independent columns of A. So you are given a matrix A. Now you view it as a collection of columns. Okay. Now you choose some of them. Okay. And check whether it's a linear, they are linearly independent or not. Okay. For example, if you choose one non-zero column, then definitely it is linearly independent. Okay. Now you choose sum 2. It's a linearly independent, but you consider every choice of 2 vectors, and they are linearly independent. Then the rank of the matrix is at least 2. Now you consider 3, 4, okay, something like that. So eventually you choose some n, okay, columns, and you find that they are linearly independent. Then actually the rank can be set n. Okay. Now this is an example. A square matrix is non-singular, okay, if its rank is n. By the way, when you see this one, okay, this is a definition. Okay. Okay. You have a lot of bullets here. Some of them are definitions. Some of them are consequences of some definitions. Okay. Here, this is the definition. So if I were you, I will write here DEF to clearly see that this is a definition. The reason why I emphasize this is this. When I took this course, this was the second math course. Okay? The first one was the linear algebra in the graduate school. But at that time, I didn't read the textbook carefully. Okay? But this course was intense to me somehow because of the professor's style. And I really felt uncomfortable with this sentence. Because I believe that this must be if and only if. Okay? So if rank of a square matrix A equals n, then it's a non-singular, invertible. Okay? But this is actually kind of how to say it, definition. Okay? So when you have a definition, if means if and only if. Be careful. Okay? So in the definition, if you want to imply if and only if, you don't need to write if and only if. You just write if. Got it? So this is if and only if for the definition. By the way, this sentence has if and only if. What does that mean? If this sentence is written precisely, this is not a definition. This is a lemma, proposition, or a theorem. What does that mean? It's a consequence of some definitions. Got it? But be careful. If some sentence has if, okay, it may not be the if in the definition. Because there are some consequences that only holds for some cases. Okay? So be careful. Whenever you see some bullets in this notebook and other lecture notes, check whether it's a definition or a theorem or a lemma proposition. Got it? Okay. Otherwise, you will get confused a lot. By the way, to understand this consequence, okay, you have to know the definition of a determinant of a square matrix. Okay, the textbook has it. Okay, so you read the textbook. Okay, next one, section 2.4, inner product and norm. Okay. So only the vector norm is presented here, but the textbook also has sections for matrix norms. What I remember is that in this textbook, matrix norms do not appear frequently. But anyway, you need to know. Okay. But vector norms appear too many times, so we need to review the definitions. Okay. So suppose we have same length vectors. Okay, same. Okay. Then we can define, see that? We can define the inner product of these two. Okay. Sometimes it is denoted like this, or sometimes this one. And as you see, what is this? Summation of products, right? So whenever you see this one, write this way. If you are from a physics department, probably you prefer this one. But don't try. This is better. Okay? Anyway, it's kind of clear what happens. Okay? So here comes suddenly a question. What does that mean? The author of this lecture note, which actually he's the first author of the textbook, wants you to find the properties of inner products yourself, okay? Not in the class meeting. Okay. So here comes another definition. So given a real n vector x, its norm is defined this way. Especially this norm is so-called Euclidean norm or 2 norm. Okay. There are other definitions as P norm with a real number P greater than or equals to 1. Okay. So there is 1 norm, 1.5 norm, there is a square root 2 norm, got it? Okay. Any real number can be defined by extending this one, but among them, the 2 norm or Euclidean norm is the most important one. And this is what you know, okay? Norm of x is the distance from the origin to this vector x in the Euclidean n space. So as you see, there is a square. So it's actually from the Pythagorean theorem. Got it? What are the properties of this 2 norm? You read it. You read the textbook. Okay? And we also have orthogonality of 2 vectors. So this is definition. Okay? That's why here this if means if and only if. Okay? If 2 vectors are orthogonal, then this holds. Or this holds, then these 2 vectors are orthogonal. Okay, so chapter 2 is covered. Let me quickly emphasize some other terms you have to read in chapter 2. Okay, so now you should understand these terms like subspace, span. Okay. So section 2.2, section 2.1. Of course, determinant of a matrix in section 2.2. Cauchy-Schwarz inequality. Cauchy-Schwarz inequality in section 2.4. Also, as I just said that any real number p greater than or equal to 1 can have a well-defined p norm. Actually, there is another one called something like this, infinity. By the way, to denote that index for the p norm, we use subscript, because superscript may be confused as a power. Okay, it could be misunderstood as an exponent of something. Okay, so this means 2 norm, but throughout the text we will just drop it, because if we do not specify the number p, then it's 2 norm. Okay. Anyway, infinity norm is interesting, and you'd better know. Okay. And what else? Yeah, there, that's done. Okay, chapter 3. Okay. Chapter 3 is again about the transformations. Some of them are linear transformations, and some of them are not. Okay. The emphasis is on linear and quadratic, these two things. So let's take a look at the lecture note. So first, the authors talk about linear transforms, and here comes the eigenvalues and eigenvectors. Why this is so important, eigenvalues and eigenvectors? When we transform a vector of length n using an n by n matrix, okay, then this notion is very interesting. If you remember, the story is like this. So this linear transformation with square matrix, not only square matrix but especially square matrix, is related to something like this. So you have input to a linear system, and you have an output of a linear system, and suppose they are both members of Rn. Okay? And then linearity of this system, if and only if there is a matrix A, which is n by n, such that the output is this A times x. Okay. Probably your linear algebra class never proved this one, but if I teach linear algebra, I will prove this one. This proof is not that difficult, but you should remember. Okay? The reason why you learn the linear algebra is to learn a linear system with vector input and vector output. Okay? Got it? You always have some matrix that relates the input and output of this linear system. Okay? And especially when these two vectors are of the same length, then something surprising is there. Okay? What can we do? Interestingly, some vectors, not every, some vectors applied to the input to the system appears at the output after some non-zero scaling. Okay? There are some such vectors. Okay? These are called what? Eigenvectors of this matrix. So you find, let me see, V, I remember. You find some vector V, okay, that satisfies this one. Okay? What does this mean? Okay, see that? Now view this one, okay? Probably you have done it already, okay? Or now you start to do it. Okay? Whenever you see something like this, now as an electrical engineer, not as a Department of Mathematics or electrical engineering freshman, okay? You are a graduate student. Whenever you see this, okay, this is the input to a linear system, okay? And the linear system is characterized, the input-output relation is characterized by this matrix. Now this is the output. Output is proportional to the input, okay? So if the output of a linear system is proportional to the input, then every time you have see something like this, not only with vectors but also with some signals, you call this input as an eigenfunction, or in this case eigenvector. Okay? And the corresponding this constant is called eigenvalue. Okay? Got it? And you find many of these. For example, if Vi is an eigenvector, any constant multiple of Vi is also eigenvector. So actually, if you can find at least one eigenvector, there are uncountably infinite number of eigenvectors. However, such eigenvectors, just the scaling of this one, you can just represent all of them with some unit norm vector, right? So you have only one. But you can find some non-proportional to this eigenvector. So you count them. Okay? Surprisingly, what people have found is that if you count them, you always have finite number of such eigenvectors with unit norm, not proportional to. Okay? Interesting. That's why I use index I. Okay? Usually, if I use index I, it means finite or countable. Anyway, I will not talk about eigenvalues and eigenvectors any longer, except what appears in the lecture note, because in order to do that, I need the entire semester to talk about eigenvalues and eigenvectors. Anyway, so whenever you see some matrix A, now you view it as what? A linear system. Okay? That's my message, you remember, from today's lecture. Okay, so here I want you to underscore this part, non-zero. Okay, non-zero. Okay. So eigenvector must be a non-zero vector. And as you see here, what does this mean? The output of the linear system is proportional to the input. Got it? And this is the proportionality constant. By the way, if you move this to the left-hand side, and if you factor this V out, how can you do that? You view this lambda times V as lambda times identity matrix times V. In that case, you can write it as what? Parenthesis open, A minus lambda times the identity matrix, parenthesis close, and V equals 0. From that property, so if the V is an eigenvector of the system or the function, then what happens? A minus lambda I times V equals 0. And that reminds you something related to the definition of linear independence, right? Because we said that if V is an eigenvector, it's non-zero. Okay? So V is non-zero, but you want A minus lambda I times V equals 0. What does that mean? A minus lambda I must have linearly dependent columns. Okay? So actually this is related to the previous linear independence of columns of a matrix. Especially in this case, we assume A is scalar, so lambda is an eigenvector of A if and only if lambda A minus A is singular. Okay? And we define the definition of singularity in terms of rank. Okay? Anyway, so this is the notation. And if you write this one, okay, using the definition of determinant, it's a polynomial in lambda. Okay? So this polynomial is called characteristic polynomial. Okay? And this polynomial of order n may have maximum distinct roots n. Okay? Sometimes the maximum distinct roots may be less than n. In that case, what? In Korean, we have 중근, right? Okay? In that case, such root has, we say, such root has algebraic multiplicity greater than 1. Okay? Anyway, because this is algebraic equation. Anyway, you read textbooks for the linear algebra, or at minimum, you read a textbook, okay? Our textbook. Okay? So here goes another question the author wants to ask you. Okay. Now, the reason why we talk about symmetry matrices is that there are two reasons. One is it itself is very important in the linear transformation. Also, it's very important in so-called a quadratic form. That's why the authors talks about this symmetric matrix. Okay, symmetric matrix is defined as a square matrix that equals to its transposition. Okay, so the mnth entry has the same value as nmth entry. Okay. And here goes interesting definition. Okay, and time's already up, so I want to be quick. But whenever you have matrix, okay, consider an extreme case where this number of columns and rows is 1. What does that mean? It's a real number in this case. Okay, so we have constant q, and it's positive definite if q times x squared is always greater than 0 for all non-zero x. What does that mean? As you remember from high school math, a quadratic function, actually if q may be 0, so looks like this one, or this is origin, or constant 0, or this one. Okay? What corresponds to positive definite? This one. Okay? So actually, this positive definiteness of a symmetric matrix is an extension of that notion. Okay, you have a second order term. Okay, y equals qx squared. Okay, a graph. Okay, the simplest quadratic equation, right? With what? Positive q. Okay, the extension of that notion. Okay, positive semi-definiteness is a little bit difficult because you cannot just extend it that way. Okay. So the difference is that here you have no equality, but here you have equality. And here all non-zero vectors, and this may include zero vectors. But you may say that all non-zero vectors, it doesn't matter. Okay? Anyway, you can similarly define negative definiteness and negative semi-definiteness. Okay? So you read this part. And then you move to quadratic functions. Okay? Oh, how can I handle this one? Okay. Probably we need some makeup. Okay. Okay. So this is a quadratic function. Okay. This is a function of a vector R in Rn. Okay. 2R. Okay. And here goes actually a symmetric matrix. But if you read the textbook, actually you don't need a symmetric matrix. But any square matrix can be written as a summation of its symmetric component and skew or anti-symmetric component. If you compute this quadratic term, only your symmetric component remains. Okay? So you can, without loss of generality, assume Q is symmetric. Okay? That is written and actually explained in the textbook. Okay? Anyway, if you write it down by decomposing these components and entries, then you will see what? Some algebraic equation in terms of components of x with the highest order n, if Q is an n by n matrix. Okay? So this is an extension of what you already know from high school, okay? Where you had only one variable, but here you have maximum n variables. Okay? So this figure from the textbook is an example where you have s is a member of R2. Okay? So actually you have two x's. So this is a domain, two-dimensional space, and you have a function that is a real valued 1. And in this case, Q is positive definiteness. What does that mean? If you cut through any plane, actually you have this quadratic function that increases to the both extreme, something like that. By the way, this quadratic function is very, very important because it is used to test the algorithms. Okay? So suppose you devised an algorithm, some optimization algorithm, and if it does not work well with a quadratic function, that's useless because this is the simplest function. Okay? So if your algorithm does not work to the simplest case, it's useless. Okay? So you will see a lot of examples in the textbook that use quadratic forms. So get quickly acquainted with quadratic forms. Okay. Okay, and you read these things. Okay. So it seems that I covered up to chapter 5. Although I'm running out of time, let me be somehow try to helpful to you. So in chapter 4, also you have to read chapter 4. I will write down some terminologies I want you to remember from chapter 4. Okay. So you have to differentiate this, distinguish these two terms: straight line, a straight line, and a line segment. Okay. This is translated as 직선, and this is 선분. Got it? Okay. You have to differentiate. Okay. And also, there are terminology like hyperplane and hyperspace. Let me see. Half space. And also linear variety. And convex combination. Of course, convex set. Extreme point. And interior point. Boundary point. Okay. So probably you'll find that, hey, it seems I have to read all of them. You are right. And polytope and polyhedron. Okay. So these are what you need to know from chapter 4. Okay. Okay. Time's up now. And from chapter 5, I don't know how do I handle this one. Yeah. Okay. Anyway, that's all for the day.